Following lecture is going to be a quick, short and precise crash course on Group 2 elements. So here are all the Group 2 elements, beryllium, magnesium, calcium, strontium, barium and radium. Here I've written down the electronic configuration of all the elements in Group 2. Beryllium is 4 electrons, 1s2 and 2s2. Magnesium is 12 electrons, so that's 1s2, 2s2, 2p6 and 3s2. And as you can see, if you go down the group, the shells keep on increasing and you have more and more electrons. But what you're going to notice is that each element has the outermost shell has an s subshell with 2 electrons in it. So all these elements have an s subshell with 2 electrons in the outermost shell. So strontium has 5s2. The shell number keeps on changing, but each element has an s subshell with 2 electrons in it. And over here I've drawn the simplified electronic structure of both of all the elements. So just to show you the trend, I've drawn the electronic structure of beryllium, magnesium, calcium and strontium. You're going to notice is that each element has 2 electrons in its outermost shell. Just as I stated earlier, 2 electrons in their outer shell. So all of them have 2 electrons in their outer shells. Based on these electronic structures, one trend that you're going to notice down the group is that the number of shells keep on increasing. If the number of shells keep on increasing, there's going to be increased shielding effect, which basically means that the outer electrons are not going to be attracted by the nucleus very strongly, because you're going to have all these electrons in the middle that will come in the way and that will shield the outer electrons, and the attraction of the nucleus is going to decrease for those outer electrons. For example, if you look at strontium over here, strontium and the outer electrons, the attraction between the nucleus and the outer electrons is going to be lesser because there are lots of different shells and electrons coming in between. So the outer electrons will not be very strongly attracted to the nucleus. Whereas in beryllium, the outer electrons and the nucleus are, there are lesser shells in between them. So the attraction or the shielding effect is going to be lesser, and the attraction would then therefore relatively be stronger with the nucleus. The trend that you're going to notice is that the atomic radius also increases. The atom size actually becomes bigger because of more shells, so the electrons are further away from the nucleus. So they're going further and further away from the nucleus. Beryllium's electrons are very close to the nucleus, whereas strontium's outer electrons are very, very far away from the nucleus. Because of this extra distance, the electrons are not going to be attracted very strongly to the nucleus. So there are two factors. These two factors over here. The electrons are very far away from the nucleus, so the attraction is lesser. Plus, there are lots of different shells coming in the way, so the shielding effect is greater. So the attraction of the nucleus to these outer electrons decreases. So as you move down the group, the first ionization energy is going to decrease. It's going to become easier and easier to remove electrons. It's going to be very easy to remove electrons from strontium because the electrons are very far away and the shielding effect is greater. It's going to be difficult comparatively to remove electrons from beryllium because the electrons are much closer to the nucleus. There would be more attraction, and the shielding effect is also lesser. So first ionization energy decreases down the group. One factor is going against that, and that is the number of protons. As you go down the group, the protons keep on increasing. So two factors support the fact that there's going to be lesser attraction for the electrons and the nucleus. There's only one factor, which is protons. Because there are more protons in strontium, the attraction for electron is going to be greater. But since two factors are in against the fact that the attraction is going to be greater, so overall the ionization energy decreases. It becomes easier and easier to remove electrons. Another thing that should be noted is that for each element, getting rid of the first 2 electrons is the easy part. These electrons are furthest away from the nucleus, so removing those electrons, the outer 2 electrons, is going to be relatively easy. Whereas removing the third electron, you would have to come closer to the nucleus. The electrons would be closer to the nucleus, so removing the third or the fourth or the fifth electrons, they're going to be difficult. So each atom, when it ionizes, it usually loses just 2 electrons, and they always form +2 ions. So getting rid of the first 2 electrons, that's going to be relatively easier compared to removing the other electrons, because as you move closer to the nucleus, the attraction is going to be stronger. There's going to be lesser shielding. So usually form +2 ions. All these elements, they usually form +2 ions. I've written this down as well. +2 ions are formed as removing the first 2 electrons from the outermost shell has a much lower ionization energy. Here I've posted a chart that shows the first ionization energies and quotes the values. So you can see the trend down the group. As you move down the group, the ionization energies, first ionization energies specifically, are decreasing. Remember, these values are available in your data booklet as well. So make sure if any question is going to ask you about ionization energy values, you can get these values from the data booklet. And here I am going to quickly quote the values for the successive ionization energies, which is that you're constantly removing electrons from magnesium. Removing the first two electrons is going to be very easy because of the higher shielding effect, and the distance from the nucleus is also greater. So I've quoted the value for magnesium. The first ionization energy is 736 kilojoules per mole. The second one is 1450. And over here, you're going to notice as you move from the second ionization energy to the third ionization energy, there's a drastic increase, a big jump in ionization energy, which means that the electron is now closer to the nucleus. It becomes more difficult to remove the electron. So removing the third electron is actually becoming more difficult. So first two electrons, it's easy. Removing the third electron immediately becomes very difficult, and removing the fourth and fifth, so the inner electrons, it becomes difficult, which is why magnesium usually loses only the first two electrons, because losing those two electrons is going to be relatively easy. Next thing that you should learn about group 2 is that the reactivity of the metals increases down the group. So as you move down the group, the size of the atom becomes bigger and bigger, and as we have discussed previously, it becomes easier to lose electrons. So down the group, reactivity increases, bigger atoms, more shielding, more distance. It's easier to lose electrons, and whenever metals, they have to react, they always lose electrons or they get oxidized, which makes metals good reducing agents because they're always losing electrons or they're giving electrons to other elements. So they're good reducing agents, but the power or reducing power actually increases to the as you move down the group. That you should know is that group 2 metals, they form a giant metallic lattice, and they have strong metallic bonds in that giant metallic lattice. What is meant by the term giant metallic lattice is that you have positive metal ions in a sea of free moving electrons in that giant metallic lattice. So you have a lattice of positive ions. All the elements, all the metals, they would like to lose electrons. Group 2 metals would form positive 2 ions. So they would all form positive 2 ions, and they would lose electrons, and those electrons would be randomly moving around. They would be delocalized. They would be free moving electrons. So they would be freely moving around, and there would be a strong force of attraction between the electrons and the positive ions. So the electrons would be acting as a glue that would keeping the whole structure together. As you move down the group, what happens is that the size of the ion becomes bigger. The metallic lattice is exactly the same. The same ion is formed, plus 2 ion is formed. The same number of electrons are delocalized. But what happens is that if you have bigger ions, the charge density is going to be lesser. The distance between the delocalized electrons and the ions is going to be greater. So the attraction is going to be weaker between the positive ions and the delocalized electrons. So bigger ions, the positive charge is more spread out. It has a lower charge density, and because of the greater distance between the ions and the delocalized electrons, the attraction would be lesser. So as you move down the group, the lattice is going to become weaker and weaker. So the what effect would that have on the physical properties is that the melting points and the melting point specifically would decrease. Here I've drawn a graph of the melting points of the metals in group 2. What you notice is that the general trend is that the melting points are decreasing. Bigger ions, there would be lesser attraction in the metallic lattice because of the lower charge density. So the general trend is that the melting points are decreasing. But Mg over here is an anomaly. It doesn't follow the trend exactly. The reason why Mg has a lower melting and boiling point is because it's the metallic bonds are not just an attraction between positive ions and delocalized electrons, but also because of the three-dimensional crystal geometry, the arrangement of how in the three-dimensional space, how are the ions arranged to each other. By arrangement, what I mean is how are the ions stacked together against each other. So for Mg, the arrangement is different compared to the others, and that arrangement leads to a weaker metallic lattice, which is why Mg has a lower melting and boiling point. Next reaction that we're going to study is the group 2 metals reaction with oxygen. Now, all group 2 metals, they burn with oxygen, they produce their oxide, and all the oxides are white solids. So magnesium reacts with oxygen to produce MgO. Calcium similarly reacts, burns in oxygen to produce calcium oxide. Similarly, strontium oxide and barium oxide are produced. You should also know that the reactivity of this reaction increases down the group. Mg is less reactive. Its reaction with oxygen is slightly relatively slower, whereas barium is more reactive. Its reaction with oxygen is relatively faster. Next reaction that we'll study is the reaction of group 2 metals with water. All group 2 metals, they react with water to produce hydroxide, and hydrogen gas is given off. So Mg reacts with water to produce MgOH2. Similarly, calcium reacts with water to produce calcium hydroxide, and hydrogen gas is given off in each case. Again, you should know that as you go down the group, the reactivity of this reaction increases. Barium is going to react vigorously with water, whereas Mg is going to be reacting relatively slowly with water. The first element, magnesium, has a very slow reaction with cold water. It has a very slow reaction with cold water. So when the water is cold, there's hardly any reaction. Hence, it reacts with steam at high temperatures. So you need very high temperatures for this first reaction, and water is usually in the form of steam for this reaction to happen at a considerably faster rate. As you move down the group, calcium, on the other hand, reacts slowly with cold water, but the reaction is still noticeable. It's noticeably faster than magnesium, so you can see a lot of bubbles being formed. So, calcium will react with cold water, but it's going to be much more vigorous when the water is hot at higher temperatures. And the last two elements, as you keep going down the group, the last two elements, strontium and barium, are going to have vigorous reactions. Even with cold water, the reaction is going to be very fast, and you're going to see a lot of bubbles being formed of hydrogen gas. Another point that needs to be mentioned is that in all the four reactions, hydroxides are formed. Remember this, that the solubility of the hydroxides increases down the group. As you go down the group, this hydroxides become more soluble. The last two, strontium and barium hydroxide, are very soluble, whereas magnesium hydroxide has very less solubility. And calcium hydroxide is partially soluble. So since these are hydroxides, they're going to form alkaline solutions. Magnesium hydroxide is very less soluble, so its pH is around 8. It doesn't ionize, it doesn't produce a lot of OH ions. As you go down the group, calcium hydroxide becomes more soluble, strontium hydroxide, barium hydroxide are very soluble. Their pH, they dissociate in water, they dissolve in water, they produce a lot of OH ions, so their pH is greater than 10. So barium hydroxide is going to have a pH that is going to be very close to 14. So remember this, that these three, the bottom ones, are going to be strongly alkaline or relatively strongly alkaline, whereas magnesium hydroxide is going to be very slightly alkaline. Now, along with hydroxides, you must also know the solubility of sulfates, which is the opposite of hydroxides. For hydroxides, the solubility increases down the group, but for sulfates, the solubility is decreasing down the group. Barium sulfate is insoluble and usually forms a white precipitate that is clearly visible. MgSO4 is very soluble. So as you go down the group, the solubility increases. Calcium sulfate is partially soluble. Strontium sulfate is also somewhat, you can call it insoluble. And barium sulfate is completely insoluble. To discuss the thermal decomposition of nitrates and carbonates. So all group 2 carbonates and nitrates, they decompose when they are heated. So firstly, a group 2 metal carbonate, for example, magnesium carbonate over here, would decompose to produce a metal oxide and carbon dioxide. All group 2 carbonates are going to decompose in exactly the same way. A white solid is going to be produced and carbon dioxide gas is going to be given off. So all equations are going to be similar. And the decomposition of the nitrates, a group 2 nitrate is going to decompose and produce a metal oxide again. A brown NO2 gas would be produced and a half O2 gas, half O2 or oxygen gas molecules would be produced as well. So remember this gas over here is going to be a brown gas, and all oxides that would be produced, they're going to be white solids. Over here, I've posted a table of the decomposition temperature of the carbonates first. So, decomposition is going to become more and more difficult as you descend group 2 for carbonates. If you look at magnesium carbonate, the decomposition temperature is 540. For calcium carbonate, the decomposition temperature is 900. And as you move down the group, the decomposition of carbonates is going to become more difficult. So decomposition becomes more difficult. One thing that you should note is that the first two carbonates, magnesium carbonate and calcium carbonate, they would decompose in a Bunsen flame. A Bunsen flame usually has a temperature of 1000 degrees centigrade. So their decomposition temperature is lesser than 1000 degrees centigrade. So they would decompose in a Bunsen flame. Whereas the bottom two carbonates, they have a higher decomposition temperature. So they would require a much higher temperature. So these two are not going to decompose in a Bunsen flame. I've also written down the decomposition temperatures for the nitrates. And as you can see, the thermal stability increases down the group. Magnesium nitrate decomposes very easily, whereas barium nitrate requires a much higher temperature for decomposition. And the same very concept could also be applied to the decomposition of hydroxides, group 2 hydroxides. Remember, group 2 hydroxides, they decompose to form a metal oxide and a water molecule. And if you, and this is a reversible reaction, so if you add water back, they would form a hydroxide back again. So heating converts a hydroxide into oxide, water leaves off, and adding water converts it back into a hydroxide. So again, as you can see, the decomposition temperature increases down the group. magnesium hydroxide decomposes very easily, whereas barium hydroxide decomposes at a much, much higher temperature. The next thing that we're going to discuss, they're called flame tests. In flame tests, what happens is that you take a nichrome wire, you clean it with HCl, and you dip it in a salt which contains one of the group 2 cations. And those cations, when that nichrome wire is placed in a luminous Bunsen flame, then it gives you different colors. So what happens is, if you put a magnesium salt and you put it in a flame, you're going to get an intense white color, which is shown over here. Similarly, if you do a flame test with calcium or salt containing calcium ions, you're going to get a brick red color of the flame, which is shown over here. Then you have strontium. If you do a flame test with strontium, you're going to get a scarlet red color, as shown over here in this image over here. And with barium, you're going to get an apple green color. So you must remember all these flame tests. These are the flame tests. They help you identify the cations, whether it's a magnesium, calcium, or strontium, or barium cation that is present in a salt. We will now try to discuss the uses of some group 2 compounds and group 2 elements. So the first compound that we're going to discuss is magnesium oxide. Magnesium oxide is a ceramic material. It has very high melting point, and it is a very good electrical insulator as well. Now, the reason why it has a very high melting point and it's a good electrical insulator is that it's a giant ionic lattice where you have +2 ions and -2 ions, and they would be strongly attracted to each other. So as you can see in this giant ionic lattice diagram, you would notice that the +2 and -2 ions, they would be tightly packed together, and the -2 ions would be strongly attracted to the +2 ions, which is why it's going to have a very, very high melting point. Now, the property high melting point, it has a significantly high melting points compared to the other substances. So it's used as a refractory material was in crucibles and in furnace linings where high temperatures, they're very high temperatures. So you want the lining, etc., or the substance that they are made from, you don't want it to melt. So you make it out of magnesium oxide. Similarly, the property of being good electrical insulators, they're therefore used as protection for high voltage industrial cables, and you can also use them to make fire alarms because they have high melting points and they're not going to be conducting electricity, so they would be suitable for protecting these cables. I'm going to discuss the uses of lime and limestone. Lime is calcium oxide, and limestone is calcium carbonate. Now, both of them are used to reduce acidity in soils. So they are going to react with the H+1 ions in the soil and CaO, calcium oxide, or calcium carbonate. These are both basic in nature. Bases would react with H+1 ions, and they're going to neutralize that. Water would be produced with carbonates. Water and carbon dioxide is also produced. So both of them are used to remove acidity in soil. So if the soil becomes acidic because of acid rain, you can get rid of the acidity by adding calcium carbonate or calcium oxide. In a similar way, they also used to remove acidic gases from waste gases. Very common acidic gases are sulfur dioxide and nitrogen dioxide. They're going to react with the basic calcium oxide, or you can also use calcium carbonate over here to produce the salt calcium sulfide or calcium nitrate. So a similar reaction could also happen with calcium carbonate or limestone. So I've written down the equations: calcium carbonate reacting with sulfur dioxide producing calcium sulfide, the salt, and carbon dioxide gas would be released as well. So with carbonates, carbon dioxide gas would be released. Same with calcium carbonate plus NO2, calcium nitrate would be produced, and carbon dioxide gas would be released as well. There is one problem that is associated with calcium oxide and soils. And that problem is that calcium oxide, which is basic, it's going to react with ammonium fertilizers. So fertilizers containing ammonium ions or ammonium salts, they will react with calcium oxide, and the reaction would be that the ammonium ions in the fertilizer, they would act as Bronsted-Lowry acids. They would lose their H+1 ions, and those H+1 ions would react with the oxygen ions from calcium oxide to produce water. And if NH4+1, because it's behaving as an acid with this base over here, so if it loses its H+1, it would form NH3. So water, a neutralization product would be formed, water, NH3 gas would be formed, and calcium ions or a salt of calcium ions would be formed as well. So ammonium ions would start acting as Bronsted-Lowry acids. They would start releasing their H+1 ions, which would react with O-2 ions from the base to produce H2O and NH3 gas. So the problem with this is that the NH3 is going to be removed. It's a gas. It would be removed from the soil, and plants need nitrogen. So all the nitrogen is going to escape. So NH3 gas escapes and it decreases nitrogen content, and plants need nitrogen for growth. Another very important use of lime and limestone is that they are important constituents of cement. What happens is that the lime, which is CaO, is soluble, is somewhat soluble in water. So the lime, when it's mixed with water, it forms a soft mixture of, and you include sand and other substances in it as well. And this mixture then reacts with CO2, carbon dioxide from the atmosphere, and it sets and ends up forming calcium carbonate or limestone, which is a much harder form.